Transformer. A transformer is an AC static device which transfers electric power from one circuit to another. It can raise or lower the voltage in a circuit, but with a corresponding decrease or increase in current. Here, it is worth mentioning that while transferring the power, frequency is not altered. It works on the principle of mutual induction. Any transformer has two coils electrically insulated but magnetically linked. The energy from one coil is transferred to other coil by means of magnetic coupling. The coil which receives energy from an AC source is called primary coil P, and the coil which delivers the energy to load is called secondary coil S. There are two types of transformers: 1. Core type and 2. Shell type. 1. Core type. In this type, the iron core is largely surrounded by the coils. In order to reduce eddy currents, the iron core is built up of laminations. 2. Shell type. In the shell type, the coils are very largely surrounded by the iron core. This provides two magnetic circuits in parallel. The circuit symbol for a transformer with an iron core. A transformer operates on the principle of mutual induction. When an alternating voltage is applied to the primary, an alternating current is set up in it. It produces alternating flux in the core. This alternating flux links with the turns of the secondary coil. Since the flux is alternating in magnetic, it induces a mutually induced EMF in secondary of the same frequency as the flux. This follows from the Faraday's law of electromagnetic induction, that is, E equals to m into di by dt. Because of this induced EMF, the secondary coil is capable of supplying current and hence energy. EMF equation. We know that the primary voltage V1 is absorbed in circulating the primary current against the EMF induced by the main flux. This EMF is given by induced EMF equals to minus rate of change of flux, E equals to minus n d phi by dt, equation 1, where E is instantaneous value of induced EMF in volts, phi is instantaneous value of mutual flux, n is number of turns in the coil. Now, since the voltage applied is sinusoidal, the flux produced is also sinusoidal in nature. This flux is of the form phi equals to phi naught sine omega t. Phi equals to phi naught sine 2 pi f t Webers, equation 2, where phi naught is maximum value of flux, f is frequency of the supply. This alternating flux induces a self-induced EMF in the primary winding, a mutual induced EMF in the secondary winding. N1 and N2 be the number of turns of P and S respectively. E1 equals to minus N1 d phi by dt equals to minus N1 d phi naught sine 2 pi ft by dt equals to minus N1 of 2 pi f phi naught cos 2 pi ft. E1 equals to N1 phi naught 2 pi f sine of 2 pi ft minus pi by 2 volts. Thus, the induced EMF in a coil lags the flux induced by an angle of 90 degree or pi by 2 radians. E max equals to N1 phi naught 2 pi f volts. E RMS equals to E max by root 2 equals to E1. E1 equals to N1 phi naught 2 pi f by root 2. E1 equals to 4 by 44 phi naught N1 volts. Equation 3. This is known as EMF equation of the transformer. Similarly, we can write the mutually induced EMF. E1 equals to 4.44 phi naught N1 volts. Equation 4. Dividing equation 4 by equation 3, we get E2 by E1 equals to N2 by N1 equals to K. Equation 5. K is called as transformer ratio. The efficiency of transformer is defined as the ratio of the output power from the secondary to the input power of the source. For an ideal transformer, output power equals to input power. Input power equals to E1 I1. Output power E2 I2. For an ideal transformer, output power equals to input power. E2 I2 equals to E1 I1. E2 by I1 equals to I1 by I2. Equation 6. From equation 5 and 6, E2 by E1 equals to N2 by N1 equals to I1 by I2 equals to K. Equation 7. The induced EMF E2 has a phase difference of 180 degree with respect to E1, that is E1 and E2 are out of phase. Similarly, the induced current in the secondary has a phase difference of 180 degree with respect to the current in the primary. Step-up transformer. If N2 greater than N1, K greater than 1, the induced EMF across the secondary is greater than the EMF applied to the primary, that is E2 greater than E1. From the equation 7, it is clear that primary current is greater than the secondary current. Such a transformer is called step-up transformer. A step-up transformer consists of primary coil of thick insulated copper wire of small number of turns so that it can carry large current at low voltage. The secondary coil is of thin insulated copper wire of large number of turns of carry a small current at high voltage. Step-down transformer. If N2 less than N1, K less than 1, the induced EMF across the secondary is less than the EMF applied to the primary, that is E2 less than E1. From the equation 7, it can be seen that primary current is less than the secondary current. Such a transformer is called step-down transformer. A step-down transformer consists of a primary coil of thin insulated copper wire of large number of turns so that it can carry small current at high voltage. The secondary coil is of thick insulated copper wire of small number of turns to carry a large current at low voltage. Transformer loses. In practice, the power output in the secondary is always less than the power input in the secondary because of the losses. The losses are 1. Copper losses. The primary and secondary coils have some resistance in addition to the inductance. When current flows through the primary and secondary coils, some power is lost in overcoming the resistance as heating effect. These losses in the two coils are called copper losses. 2. Coal losses. The hysteresis. Hysteresis is the lag of magnetization behind the magnetizing field when a ferromagnetic material is subjected to an alternating magnetic field. The graph between the magnetizing field H and intensity of magnetization, and eddy current heating losses in the core of the transformer are called core losses. The hysteresis loss is minimized by selecting a material that has narrow hysteresis loop. The eddy current loss is minimized by using laminated and insulated core. 3. Magnetic leakage. These losses are due to the leakage of magnetic flux between the primary and secondary coil. That is, the magnetic flux produced by the primary does not pass completely through the secondary. If the coils are interwound, this loss can be minimized. 4. Humming losses. Ferromagnetic materials undergo a small mechanical change when magnetic fields are applied, either expanding or contracting slightly. This effect is called magnetostriction. Humming sound of a transformer is due to magnetostriction. The energy losses in producing humming sound are called humming losses. Owing to these losses of the transformer, the efficiency of a transformer is about 95%. Transformers are used in AC power distribution for the domestic industrial purposes, long-distance power transmission, welding transformers, etc. Some more important points about transformers. Turn ratio K equals to Ns by Np equals to Es by Ep equals to Ip by Is equals to square root of Zs by Zp. Therefore, Z equals to impedance. For an ideal transformer, K equals to 1. Efficiency of transformer eta equals to power S by power P. Percentage of efficiency eta percent equals to PS by PP into 100. Eta percent equals to ES IS by EP IP into 100. In practice, eta percent ranges from 75% tends to 90%. It converts magnetic energy into electrical energy. It does not amplify power.